So in my presentation, I will be talking about the Zitterbewegung Orbit of the electrons. This is a new wave function of the electrons that I believe is now for the first time can be recognized. So the structure of the talk is that I first talk about background and motivation, then theoretic foundations, the calculation, and comparison against experimental data. And so this background motivation is related to the talk that I presented at ICCF22 last year. Let's consider what is already a well-known phenomenon in the muon-catalyzed PD fusion. There it has been already in the 1950s observed that in some cases the muons will carry away all the nuclear reaction energy. This is the 5.6 MeV muons that are produced. Now the equivalent for the electrons has been observed in a Lipoglavschek study only in 2017, 2 years ago. So there the group observed that when they did PD fusion in graphite, then certain electrons were carrying away all of the 5.6 MeV reaction energy. So this observation points to the existence of an electron wave function with very close electron nucleus proximity, which allows then the electron to carry away the nuclear reaction energy. And the reason why I got interested in this field is that in our own experiments we have signals which can be interpreted as Bremsstrahlung of particles. So what we observed is in our reactions we observed the RF background to rise uniformly, and at the same time we had Geiger counting the readings about 40 times the background, and these are characteristics, can be characteristics of Bremsstrahlung. So I was interested in this topic, first to explain what we saw in our experiments. Now from the data of the Lipoglavschek study, we can right away get a crude order of magnitude estimate of this wave function we are looking for, because in the muon-catalyzed fusion, the muon takes away reaction energy in 15% of the cases, and the muon is about 250 phantom meters from the nucleus. In the Lipoglavschek study, they saw the electron taking away about 7% of the cases the reaction energy. So then, just as a very crude interpolation, we are looking for an orbit that's about 500 femtometers, just as an order of magnitude estimation. Now, my calculation is fairly simple, but to understand the calculation, you have to understand the foundations, and the foundations are not so straightforward. At least at the first sight, and this prompted me with some co-authors to write a book. So if you're interested, you can ask me about the book where the foundation is described properly, but now I try to present you in 5 minutes how I can to condense the book. So the main point is that we start from investigating Maxwell equation and talk about consequences of Maxwell equation. You might be wondering, why I talk about Maxwell equation. We all learned about it in high school already. Well, we learn in the high school about the certain version of Maxwell equation, but I think we achieved only very recently to properly understand how to write down the Maxwell equation as a field equation. So the key is that the algebra of the relativistic space-time that we live in is the Clifford algebra, and so to write Maxwell equation properly we have to work in Clifford algebra, and moreover we want to write it as a field equation. So when you write it as a field equation, then you look for objects that incorporate electric fields, currents, and charges. And the breakthrough, in my view, was done by these three gentlemen, Dr. Celani, Vassallo, and Di Tommaso. So they published in 2017 the Maxwell's equation and Occam-Razor's article, which I encourage everyone to read. And I think it's a historic achievement that this is the first time that Maxwell's equation is written as a proper relativistic field equation. So now that we know how Maxwell's equation really looks like, this is, by the way, a simple geometric picture. So if A is the vector potential and G are the electromagnetic fields, then really what Maxwell's equation is saying is that you take the space-time derivative of vector potential, you get the fields, you take space-time derivative of fields, and you get 0. So this is the simple geometric picture. Okay, but what are the consequences? There are some remarkable consequences, and I would like to just very briefly name the most important one. First, the electromagnetic Lagrangian is the simplest relativistically allowed Lagrangian formation. And in some general relativity books, you can read how Lagrangian can be derived from relativistic variation principles. So for example, in this book, the authors derive what's the simplest Lagrangian, and it's this type of expression, and this is indeed what we found, and it's a bit simpler than the traditional electromagnetic Lagrangian. The other consequence is that if you take Maxwell equation with the energy momentum squared equals mass squared condition, then this leads directly to the Dirac equation. Now, we are actually not the first ones to recognize that. There is some literature to the so-called optical Dirac equation, and the optical Dirac equation is looking at this type of equivalence in the case where there is no charges. But we can generalize this method from the case that there is no charges to the any particle case. So we see the equivalence of Maxwell's equation plus this relativistic condition with Dirac equation. And I would like to emphasize this because, of course, many physicists say that whenever you look for a wave function, you have to look for solutions of the Dirac equation. And what we are doing is not in contradiction to that, because the solutions that we get from our method are actually automatically also solutions of the Dirac equation. So I wanted to make that clear. And other important consequence is that we know what charges are made of. Charges and fields are the same thing. And we know what mass is made of. Mass is just electromagnetic energy momentum. So we really have some more clear view of some fundamental questions. Then we can recognize some interesting connections between electromagnetism and quantum mechanics. There are two key points I would like to emphasize. So the quantum mechanical probability density is the same thing as electromagnetic Lagrangian density, and this is a nice thing. So we have the wave function developing according to the Lagrangian, which is happens to be Lorentz invariant, and this happens in the case where the scalar field is 0. So what we see is that the gauge invariance is a property of the quantum mechanic wave function, but it's not, doesn't have to be an actual symmetry of the electromagnetism. The other important consequence that I will use in my talk is that we need to have a more sophisticated understanding of Heisenberg uncertainty. In our understanding, Heisenberg uncertainty applies only to those oscillation modes of the wave function which exist. So electron as a particle can have internal and orbital oscillations, and in the ordinary wave function, there is more oscillation modes than in the general solution. So you can have different solutions of the wave function with different modes existing or not existing, and you cannot apply the uncertainty principle to those oscillation modes which do not exist, only to those which are actually present in the solution. So based on these principles, Giorgio Vassallo and Di Tommaso calculated the electron structure. So very briefly, what the electron model is that you have a spherical charge surface, and it has the radius of the classical electron radius. It has a Zitterbewegung motion at the speed of light, and this radius at which it moves around is the Zitterbewegung radius. This is the reduced Compton radius. And you can recognize geometric scaling between the charge radius, Zitterbewegung radius, and the Bohr radius. And this geometric scaling factor alpha is the electromagnetic fine structure constant. So, other important point, there is equal amount of electric and magnetic field energy in the solution. So if you follow the consequences of the Maxwell equation, this is the electron model you end up with. And what I would like to emphasize about this model is that these are the values in the rest frame of the electron. But if the electron moves at some energy, then all of these values change, and there is this relativistic shifts. But the change is described by a very simple formula. So if you have a higher energy of the electromagnetic field, then the proportionality factor is just 1 over r. So, for example, if you have 2 times the electron energy than in the rest frame, then all of these values of the electron size shift by half. So it's a very simple linear relationship. Okay, and then with this background, we can finally come to the concept of the Zitterbewegung orbit. So what I was considering is, can this Zitterbewegung state of the electron realize as an orbit around the nucleus? So in that case, the electron's mean distance from the nucleus would be approximately the Zitterbewegung radius. So you can see in this picture what happens, that the electron charge moves around on this orbit, and you have this strong magnetic field in the center, and the nucleus is then in the center of this magnetic dipole field. Now let's consider the energies balances. So when the electron is at this distance r from the nucleus, then it has the electric potential energy, and the electric potential energy is described by this simple formula. So at the Zitterbewegung orbit radius I showed you before, the potential energy is about 3.7 kilo electron volts, and if it's closer, then the actual potential energy is proportionally larger than this default value. Now, how does the electromagnetic field energy of the electron change? Very simple calculation would be to say that the electron is somewhere far away at standstill, and from this stationary electron, we just let it to fall into the potential field of the nucleus. So in that case, the difference of the electromagnetic field energy would be just equal of the potential energy. But actually, we need to consider it more generally, the problem, because in the beginning, the electron does not have to be standstill. The electron can have a kinetic energy in the beginning. So that's the total energy. And in this talk, the total energy is the kinetic energy of the electron where it's at some faraway initial state. So because this total energy is an unknown term, we cannot solve yet this equation. We need a further condition, because as you can see, depending on the total energy, we can have any solution at any radius. But one important thing that I would like to point out is that this solution about the standstill Zitterbewegung, it fulfills the Heisenberg uncertainty, because the Zitterbewegung solution itself fulfills the Heisenberg uncertainty, and the oscillation in the orthogonal direction is not present. So this simple calculation is something that fulfills the Heisenberg uncertainty, But what it does not fulfill is the Virial theorem condition, because there is no particle-like movement of the electron. So, and we know that for any stable orbit, there is a relationship between kinetic and potential energy given by Virial theorem. So let's consider some solution which actually fulfills the Virial theorem as well. The solution that we will look for is a solution where this plane is rotating. So, so the electron has its Zitterbewegung speed along this direction, and it has a rotational speed along the other direction, so it becomes a rotating plane. Okay, and this is how the speeds decompose. The consequence of the Maxwell's equations is that the local speed of the electric charge is always the speed of light. And when the electron has some kinetic energy, then the speed decomposes into two directions. One is the speed along the Zitterbewegung oscillation. The other one is the speed in orthogonal to it, and this speed is the speed of the particle which gives it the kinetic energy. So I label it as these two terms, the wave speed and the kinetic speed. And the electromagnetic energy of the Zitterbewegung wave is proportional to this speed. So you can see that from the energy I had in the previous slide, this energy is reduced by this proportionality factor. So this energy of the wave is less than the energy that we had before, because the speed is less in the Zitterbewegung direction. On the other hand, it gains kinetic energy. So if we compare, the energy of this solution, which is standing still, against the energy of the rotating solution, then the difference between these two energies is what I call delta E in the presentation, right? And it comes from these two terms. On the one hand, we have the wave and the kinetic energy, and minus the energy that I had on the previous slide. And please remember that the energy I had on the previous slide is the one that fulfills the Heisenberg uncertainty. Okay, now we know what is the wave energy term. We don't know yet what is the kinetic energy term. So this is where we apply the Virial theorem. And we have to apply the relativistic Virial theorem, because the speeds are in the relativistic regime. Now, in many textbooks, the relativistic formula is written without the square. So gamma over gamma plus 1. But that formula is valid only for straight motion. When you're rotating, your motion is definitely not straight, it's circular. And for circular motion, you need to take into account the Thomas precession effect. So if you do the calculation, then this relativistic factor comes out gamma squared over gamma plus 1. All right, so now I chart here what is the solution of the total energy as a, what is the total energy as a function of the radius r at which this rotation happens. And this green line is the line that is the solution to the Virial theorem coming from the previous slide. So as you can see, we still don't know how far the electron is from the nucleus, because depending on the kinetic energy it had in the very beginning, it can have various distances from the nucleus, which all fulfill the Virial theorem. However, there is one special place, and the special place is where the delta E equals 0. So delta E equals 0 is the place where the energy of the rotating state is the same as the energy of the non-rotating state. And you can remember that this delta E equals 0 is the place where the Heisenberg uncertainty condition is fulfilled. So that's the quantization condition in this case. So we have, among all the values which fulfill Virial theorem, one special value which fulfills the quantization condition in this case. So we are almost at the solution. There is one more thing we have to consider. We have to consider the magnetic interaction with the nucleus. The nucleus is in the magnetic field of the electron, which is quite strong. So the nucleus will experience a Zeeman split. And that's a good thing because it will assume the lower energy in the Zeeman split, and this will be a stabilizing force. On the other hand, the nucleus itself has a magnetic dipole moment. So the electron feels the magnetic field of the nucleus, and it moves around in the circle in the field that's vertical, so the Lorentz force will be radial. So the magnetic field of the nucleus will add a small radial contribution that we have to consider in the Virial theorem solution. Now, that contribution of the magnetic field is quite small, but nevertheless, it makes a significant difference in where the Heisenberg uncertainty condition is fulfilled. So this slide shows our final solution. So again, the green line is the solution where a Virial condition is fulfilled. This point here is where the delta energy equals 0, and this corresponds to the fulfillment of the Heisenberg uncertainty condition. All right, so we have one special point that looks like a unique solution, and you can see that the total energy is more than 0. So what it means? It means that this is a metastable state. And it's very good news that the solution is not somewhere here, because if the total energy would be significantly negative, then this would be the ground state of the hydrogen and we would not be here. So you have to thank this relativistic effect that we are here and this is positive. So now let's look numerically what the calculation says. And this is the my calculation for the total electron energy in the beginning from which you get these stable transitions. So as you can see, the total energy depends on which isotope of the hydrogen you talk about, and the difference is the different magnetic field of the nucleus. So for the Zitterbewegung orbit around the proton, the total energy is 81 electron volts, and for Zitterbewegung orbit around the deuteron, we have 35 electron volts. What this means is that this is the initial kinetic energy. What is important is that this kinetic energy does not have to be a free electron. It can also be coming from kinetic energy of an electron orbital. Only important thing is that this is the initial electron kinetic energy. Okay, so these are some practical values we have, and now we can try to look at the validation, whether this calculation is correct or not. So the first thing that we look at is those materials where we find electron orbitals with close to 80 electron volt kinetic energy. So I have charted here some transition metals and bromine, and I have shown in the graph for different elements the energy of that electron orbital which is closest to 80. And what we actually want to see is those elements which are slightly below this line, because if you're slightly below the line, you can excite the electron up, but if you're above the line, it's hard to take energy away from the electron. So interestingly, nickel is quite close, just below 80, and I could give you, many references for nickel-hydrogen systems. Many of you have that in your lab. I choose here the Foucault reference because he was working with plain nickel. So in that case, there is no other elements. It was just nickel-hydrogen. The other interesting report is this report by a Chinese group where they observed transmutation of elements where the transmutation seemed to have catched one proton. It was in aqueous environment. And in their case, they had a bromine-based catalyst. So that report implies that bromine works, and we indeed see the electron close to 80 electron volts. Now, if this calculation is true, then it means that we have a method to somehow rationally find those LNR materials that work. So according to calculation, at least cobalt and vanadium are also pretty close, so they should be suitable LNR reactor materials as well. Now let's take a look at deuteron. So in case of deuteron, I have calculated 35 electron volt, and now I look at calcium. And in calcium, you can indeed see orbitals with very close to 35 electron volt kinetic energy. And here I would like to mention Dr. Iwamura's experiments, which were replicated by another Japanese group. And they show calcium-based material catalyzing transmutation when deuterium is present. And in the replication experiments, it was specially tested for hydrogen, and it was found that this transmutation works only with deuterium, not with hydrogen. So this again points to a validation of our calculation that the 35 electron volt is only relevant for deuterium, not relevant for hydrogen-based materials. Now, the best type of validation would come from a system where you only have protons and electrons, or only deuterons and electrons, hydrogen, nothing else. Then we can exclude some other materials, and this seems to come from hot fusion experiments. Now, did you know that hot fusion people also do LNR reactions? You might be surprised, but that is the case. It's called runaway electrons. So what happens is that in some tokamak experiments, they notice that something unexpected happens when the plasma temperature cools. So here you see a beginning, some plasma state, and they inject a puff. So they just add additional gas molecules. It's a deuterium-based plasma. And at T equals 0, so then the density of the plasma increases and the energy of it goes down because this gas they inject is cooling it. And what they observe is that when the plasma energy cools to a certain level, suddenly it starts to eject very energetic electrons. And in some experiments that I reference here, they show this electron spectrum, and they measured electron energies up to 15 megaelectron volts. So this is deuterium plasma, and in deuterium we can have, of course, deuterium-deuterium fusion. Now, what do hot fusion people do when they observe 15 megaelectron volt electrons that they cannot explain? Well, they say it's not nuclear, of course. So if you want to read some good humor, you can read how they explain that this is not nuclear. But for our presentation, we consider that this is nuclear. Another experiment that I reference here is the same thing. You have a plasma, it's a disruption, then the plasma temperature cools, which is measured by the lowering current, and then there is a plateau forming. And so during this plateau, something happens that stops for some time, the fall of the plasma temperature, and at the same time, you have very energetic electrons being produced, and this is a neutron detector that detects neutrons produced by these very energetic electrons. And what would be the most relevant is to measure the plasma temperature in this plateau. Because if my theory is correct, then it means that the plasma temperature here should be approximately 35 electron volt. Now, I did not find any literature where this was measured. And if you have any hot fusion friends, please ask them to measure this. But the closest I was finding is this article I reference here, where they, based on reactor parameters, they estimated the plasma temperature here in this regime. And their estimation was 42 electron volts, which is not bad. It's fairly close to the 35 electron volts which I calculated. Then next one is the production of energetic electrons in palladium deuterium systems. So here we are getting back to LNR again. And what we see in the photo is triple track patterns of the carbon breakup that was observed by Pamela Mosse-Bos during palladium deuterium co-deposition experiments. So it was established already, as you know, that the main reaction in palladium deuterium is the deuterium-deuterium fusion. And in that case, there is nothing that could, other than gamma photons, take away the energy, except if you have energetic electron emission. Now, to observe these carbon breakup tracks, you need some particle with at least 7 megaelectron volt energy. And this, again, corresponds to the model. So if we have electrons carrying away the 20 megaelectron volts of the deuterium-deuterium fusion, they certainly have this high energy to break up carbon particles. Now, next validation is the non-thermal. Do I have to stop here? Okay, just I'll wrap up in 1 minute. So also in palladium deuterium systems, non-thermal infrared emission was observed. Here you can see frames of this infrared emission 1 second apart. And this was also by Mitchell Schwartz observed and other experiments. Now, from my calculation, you can say what is the frequency, what should be the frequency, because this light is emitted by the nucleus due to the Zeeman splitting. So I told you that the nucleus is in the strong magnetic field of the electron, and its energy undergoes Zeeman splitting, and from Zeeman splitting, you can calculate that in proton case, the 700 terahertz is the frequency of emitted photons, and in deuterium case, 200 terahertz frequency. So I would really love for somebody to measure this. So as far as I know, these frequencies were not measured yet, and I was very happy in Dr. Kasagi's presentation yesterday that his group is planning to do spectroscopic analysis. My request, please look for the 700 terahertz peak. That's a prediction. And for palladium deuterium system, please look for the 210 terahertz peak. Yeah, then I have to skip over this slide. So this is the Holmlitz ultra-dense hydrogen. It turns out that the nucleus-nucleus distance that they measured, this 2.3 picometers, is corresponding to our model. So the Holmlitz ultra-dense hydrogen is actually the same Zitterbewegung orbit, but with magnetic interaction between them. So this is the conclusion, that we can understand this new wave function of the electron state, and this seems to be experimentally appearing in many different experiments: hot fusion, accelerator experiments, transmutation, LNR reactors, ultra-dense hydrogen. So it could be something that's quite common to LNR, and I hope in the future there will be many validating experiments to this calculation.
I'm missing one serious point. We know that the stored magnetic energy at the Bohr level is 0.057 electron volts.
Sorry, I can't hear what you're saying.
Yeah, the stored magnetic energy. If an electron moves around a nucleus, there is generated a magnetic field that contains energy.
Yes.
And at this level you show here, it's already some 100 electron volts. And this is a huge factor you just neglect.
As I showed in the presentation slides earlier, the electron's energy is half electric field energy, half magnetic field energy. So this is always, when you have an electromagnetic wave, always half of the energy of the wave is magnetic and half is electric, and this is exactly what is in our electron model.